Question 2 part A, group 2 elements show metallic bonding. Define metallic bonding. Now bonding is to do with attraction between two things. Okay, so and since we have positive metal ions and electrons, positive metal ions and electrons are negatively charged, so the attraction has to be electrostatic. So we shall say electrostatic attraction between metal ions. You can say positive metal ions and delocalized. This word is very important. Delocalized electrons. So these electrons are moving around the lattice. Then B, the group 2 elements form stable 2+ ions. Roman 1, state and explain the variation in ionic radius of group 2 elements down the group. Of course, ionic radius has to increase. So we are stating first, then we shall say ionic radius increases down the group. And then we shall say, to explain this one, extra shells are being added. Okay, extra shells, extra shell of electrons added. And when you do so, this increases. Okay, I can add this one on. This increases the shielding of outer electrons, by the inner electrons. So the shielding is actually that repulsion, because these ones are negatively charged. Okay, electrons are negatively charged, so the distance will have to continue being bigger because of that shielding effect. Okay, and the nuclear attraction decreases. Okay, so but that is enough. Then Roman 2, table 2.1 shows successive ionization energy values for beryllium. Then here you see 900 and 1760. Then this is 14. So this is a large jump here. Large jump from here to here. Okay, 1000. Here you have 14,000. You see that? It's a very large. And then here you have 14,000 and then 21,000. Okay, it's not as large as this one here. From 1,000, then you go to 14,000. So what else? They're saying use this table to explain and state the general trend in these values and the significance of the large difference between the second and the third ionization energies. Okay, so state the general trend. So the general trend is going to be ionization energies. Ionization energy increases for every after removal. Okay, then there is a large difference, between the second and third ionization energies. Okay, what is the significance of that? Okay, the significance is that the third electron is removed from the inner shell. Okay, the second and third ionization energies, because the third electron comes from an inner shell. That inner shell is nearer to the nucleus, so you receive a lot of resistance because of the attraction, okay, from the nucleus. So that is that. Part C, all the group 2 elements except beryllium have more than one stable isotope. Roman 1, beryllium exists as the single isotope, this one here. Describe the distribution of mass within an atom of beryllium. Now, we know that mass, using the Bohr atom, we have a nucleus. That nucleus contains protons and neutrons. Okay, and they have a relative mass of 1. And then electrons are in shells orbiting the nucleus. So the mass of electrons is negligible, okay? But we take the mass of the protons and neutrons. So we can say mass is centered in the nucleus. In the nucleus, where protons and neutrons reside, or you can say are, where protons and neutrons are. Okay, they have an average mass of 1. Electrons just orbit the nucleus in shells and have a negligible mass. Okay, but they say describe the distribution of mass. So the mass is at the in the nucleus, where we are seeing protons and neutrons. That's enough. Okay, there are 2 marks. You have to talk about the center, where the mass is. It is in the nucleus. So what is there? Protons and what? Neutrons. In fact, I can add on and say they have an average mass of 1. Each of them 1. Okay, like that. Each has an average mass of 1. Then next, complete this table to show the number of protons. This is magnesium. The isotopes of magnesium. So since they are all magnesium atoms, then the number of protons is the same, 12 everywhere. And then number of neutrons, we get the mass number, then minus the number of protons. So this one will be 12. 25 minus 12, you get 13. And then 26 minus 12, you get 14. Then Roman 3, figure 2.1 shows the behavior of a beam of protons in an electric field. Complete figure 2.1 to show the behavior of separate beams of neutrons and electrons in the same electric field. Label your diagram clearly. Assume that the beams of each particle are moving at the same velocity. Now, when you look at this, remember protons are positively charged. Neutrons have no charge. Electrons are negatively charged. So, when and we are supposed to label this diagram. You can see that the source is here, then when it comes, there is a bending here for the protons. Now, protons are positively charged, so if they are bending towards this side, that means this one here has to be negatively charged. This electrode here has to be negatively charged, and then this one has to be positively charged. Now, when this beam is for neutrons, because for them they don't have any charge, then this one will just continue just like that. Okay, it will just continue. I'll just put on, this one is going to be beam of neutrons. They pass through undeflected. Then we shall have, for electrons, they will come, they will bend towards this, but the bending has to be bigger. Look at this one for protons. Okay, the bending is smaller because these ones have gotten a mass. Okay, so they are heavier compared to electrons here, which don't have a mass, or their mass is so negligible, it is too small. So that means this one, the electrons are going to be deflected much more than the protons. So in your bending here, you have to make sure that you show that of electrons being deflected much more than the one of protons. So beam of electrons. So that is that. Part D, Roman 1, state what is observed when dilute hydrochloric acid is added to separate samples of barium oxide and barium carbonate. Barium oxide is a basic oxide. So when you add hydrochloric acid, they react. This is an acid-base reaction. You're going to get a salt and water. So this one will just dissolve actually. Okay? Dissolves. What are we having? Barium oxide plus the HCl. You will get barium chloride. Okay? Plus water. This equation, you don't need to write it, so I'll put a 2 here to balance. And then for barium carbonate, a carbonate plus an acid, we get a salt, we get carbon dioxide and water. Okay, now to balance this, of course, I'll put a 2 here, and I think that will be all. So this barium carbonate, you will see it dissolving, it will disappear. So I will say solid. Okay, actually, even here, let me add on solid dissolves. So solid dissolves. Okay, solid dissolves. But then since there is production of carbon dioxide, then I can also say effervescence. In fact, let me take this one away and just put it maybe down here. And effervescence. Okay. Those are the equations. This one just dissolves into this. You don't have the color of water, and what this one is going to appear as a uniform, a clear solution. Okay. And then here, because of the gas which is going to be given off, you will see bubbles coming off. So that is what we are having there, but you're not supposed to write these equations, just these observations here. All right, next, write an equation for the reaction of strontium with excess of cold water. So strontium here plus water, we get a hydroxide. Strontium is from group 2, and then plus hydrogen. So to balance this one, hydrogen is 2, and then the 2, that one becomes a 4. So I'll put a 2 here to get the 4. And then oxygen, that is a 2, and already here is a 2. So that is that. So when they tell you to write the equation of a reaction, unless they say that include oxidation states, so don't put them, okay? But of course we know this one is aqueous because hydroxides of group 2, the sorbate of hydroxides of group 2 increases down the group. So this one will appear as aqueous, this one is a gas, this one is a liquid, and then this one is a solid. You can put them there or not, okay? If you don't know the states, leave them out. Then Roman 3, state the variation in solubility of group 2 sulfates down the group. So this one decreases, okay? Decreases down the group. That's why if you have NS salt that has barium ions, because barium is down there in group 2, and then you get another solution that has gotten sulfate ions. When these two come into contact, they form barium sulfate, which is a white precipitate, okay? So formation of this white precipitate just tells you that this one is an insoluble. It is sparingly soluble, by the way. So it is gotten out by precipitation.